Hey everyone, welcome to today's Explainer. Look, we're going to jump right in. If you're looking to literally revise an entire heavy-hitting math chapter in one go, you're in the right place. Today, we're taking the complete chapter on continuity and distilling it into a short, rapid-fire revision session. We're packing all the crucial concepts, the exam secrets, the formulas, and those really vital problem-solving techniques directly from the source material into this one single explainer. So, let's get into it.
But right off the bat, before we get completely lost in complex equations and limits, I've got a question for you to ponder. How can you tell if a mathematical function is continuous without doing any math at all? Seriously, is there a way to just intuitively spot continuity before calculating even a single complex formula?
Okay, let's dive into this. The secret here is something we can call the pen test. So in the absolute simplest, most intuitive terms imaginable, a function is mathematically continuous if you can draw its entire graph without ever lifting your pen from the paper. Like if the ink flows seamlessly in one continuous, unbroken motion across the page, boom, the function is continuous. But if you have to lift that pen up to jump to a new point or skip over a gap, bam, it's discontinuous. It's great because it takes this super abstract mathematical idea and grounds it in a physical, highly visual reality that you can instantly recognize.
So, here's our agenda for this revision. First, visualizing continuous functions. Then, the golden mathematical rule, followed by the limit formula toolkit, solving exam-style questions, and finally, continuity of composite functions.
All right, Section 1, Visualizing Continuous Functions and Categorizing Graphs.
Let's look at which common mathematical functions naturally pass our visual pen test and which ones completely fail. On the left side here, we have our reliable, always continuous functions. Think polynomials, your constants, linear lines, quadratics, cubics, they just never break. Exponential curves, log functions, those V-shaped modulus graphs, and the smooth flowing waves of sine and cosine, they all pass the pen test totally effortlessly across their domains. But then, look on the right. You've got the greatest integer step functions where you literally have to draw separated steps, forcing you to lift your pen over and over. The signum function jumps all over the place, and tangent functions, they hit those vertical asymptotes and break entirely. Just by contrasting these in your head, you can honestly spot the correct answer on a multiple choice test immediately just by recognizing the shape.
Moving on to Section 2, the golden mathematical rule, the core formula for continuity.
Now, visual intuition is fantastic for quick checks, right? But what happens when you're facing a complex, piecewise equation, and you can't just easily draw it out? Well, that's when we have to shift to a rigorous, formal mathematical rule. So the crucial point is, you need an actionable, step-by-step framework to actually prove continuity. And it really all comes down to these 4 specific steps. Step 1, calculate the left-hand limit, or LHL. That's just what the function approaches as you get infinitely close to the point from the left side. Step 2, calculate the right-hand limit, the RHL, so what it approaches from the right side. Step 3, find the exact value of the function directly at that specific critical point, which we call f of a. And finally, Step 4, ensure all 3 of these values are exactly equal. LHL equals RHL equals f of a. If all 3 align perfectly, you're golden. The function is continuous. But if even one is off, the whole chain breaks.
Now you might be thinking, how do I calculate those left and right limits without getting completely tangled up in messy algebra? Well, you should rely on this incredibly consistent trick, the h substitution. You simply set x to a minus h for your left-hand limit and set x to a plus h for your right-hand limit. In this case, h is just a microscopic quantity that's approaching 0. Let me reassure you here. Using this h approaches 0 substitution makes solving these limits universally foolproof. It's a real game changer because you never have to second-guess which direction you're coming from. You just plug in the h, simplify it, and let the math smoothly reveal the limit.
Okay, Section 3, the limit formula toolkit, our essential 11th grade cheat sheet.
To actually make that h substitution work in advanced problems, you really need the right tools from your previous foundational studies. Now, what's really interesting about this slide is that memorizing these specific limits is quite literally half the battle won when dealing with 12th grade continuity. So look at this table carefully. The limit of sine x over x as x approaches 0. That's simply 1. You get the exact same result for e to the power of x minus 1 over x and for log of 1 plus x over x. Oh, and please, pay special attention to that very last one. 1 minus cosine 2 theta equals 2 sine squared theta. Trust me,
You are going to see that specific trigonometric substitution pop up over and over again in complex past year problems. Seriously, take a mental snapshot of this cheat sheet right now.
Section 4. Solving exam-style questions by finding unknowns like K, A, and B.
So it's time to showcase exactly how these concepts are tested in actual board exams, because often they aren't just going to ask if a function is continuous. Instead, they'll tell you it is continuous, and then force you to find missing variables like K, A, or B. So here is your exact workflow for solving these previous year questions flawlessly, and more importantly, efficiently. Step 1, evaluate the function, f of a, at the specific part of the piecewise equation that actually contains the equals sign. Step 2, and this is to save you major time, evaluate the limit on the opposite side of that equals sign. Like if the equal sign was bundled with the less than symbol, you only need to calculate the right-hand limit using your h approaches 0 method. Seriously, don't waste time doing both if you don't have to. Step 3, equate that newly found limit directly to your f of a value. And step 4, just solve the resulting algebraic equation for your unknown variable.
And this right here brilliantly illustrates how that workflow functions in practice. In one pretty notable example we pulled from the source, following those exact steps for a piecewise function at a critical point of 3 yielded this beautifully perfect linear relation. By setting the evaluated f of 3 equal to the calculated right-hand limit, all those complex variables just collapsed neatly into a super simple equation, a minus b equals 2/3. Getting to this clean fraction results really just proves how powerful and reliable this standardized 4-step approach is, especially when you're under the intense pressure of a ticking clock.
Let's move to Section 5 and see how this builds. Continuity of composite functions, combining continuous elements. So what actually happens when things get layered and we mix our continuous functions together? Well, the rule here is incredibly generous. If you have two functions that are already continuous, let's just call them f and g for now, then adding them, subtracting them, or multiplying them will automatically give you a brand new continuous function. Even dividing them works perfectly, as long as your denominator isn't 0, of course. And this also applies when you're nesting them. For example, x squared is a continuous polynomial, right? And cosine is a continuous wave. So putting an x squared inside a cosine function, creating cosine of x squared, means it automatically remains completely continuous. You don't even have to calculate the limits. The properties alone absolutely guarantee it.
I absolutely love this bold quote straight from the heart of our source material today. I can give you in writing, do these questions and you won't need to do any others. The real power of a hyper-focused revision like the one we're doing today is that you don't need to exhaust yourself endlessly grinding through thousands of random problems. By mastering this exact visual intuition, the golden rule, the H substitution, and that limit cheat sheet we talked about, you are going to be fully and confidently prepared for literally any trick the exam throws at you. Which brings us to our final thought. If you encounter a terrifying, multi-layered, piecewise function on your math exam tomorrow morning, what are you going to do? Will you rely on your quick visual pen test intuition to immediately spot the behavior? Or are you going to dive straight into the rigorous H approaches 0 method to systematically prove it? The best learners know exactly when to deploy which tool from their kit. So review these concepts, internalize the rules, and keep that mathematical intuition sharp. Thanks for joining this explainer,